All right, physicists, welcome to our second class of a new unit. Today I handed back tests in class. Overall, the average is very good, so you see that we're weighted here towards a lot of people getting over 90%. Quite a few people getting in that B range, and then the rest. So about kind of half and half. So if you're one of those people who's below this 70% cutoff, I encourage you to come in, get your test, do some corrections. If you can get your grade up to a 70%, that's where I would like it to be. Okay, now, last class on Monday we did quite a few new concepts. So today, a lot of this video is going to be making sure that we're clear on those concepts. The concept of center of mass, acceleration of center of mass, linear momentum, and the impulse momentum theorem. And I think the best way to do that is just to go slowly through them. So first we're going to do these two, and then we're going to do these two, and hopefully by the end of this video you're not confused about that. And then we're going to introduce a couple of new ideas having to do with momentum conservation. So, first off, the center of mass is a weighted average where the mass of where the mass in a system is located. So it's a point in your system, and if most of the system mass in your system is concentrated around one place, that's where your center of mass is going to be close to. So for instance, the Earth and the Sun have a center of mass, and it's real close to the center of the Sun. When the Earth goes around the Sun wobbles a little bit, but the Earth is going in a big swinging circle around it. The center of mass of the entire system, it doesn't move a lot. And so that's a interesting point. The center of mass is special in that you add up all the forces on particles in the system. It acts like a new particle that follows F equals ma, where m now is the total mass of the system, and F net is the sum of all of the forces on all of the particles. So as we'll talk about later in this video, the only way you can get a net force on a particle is for that force to be applied by something that we consider to be outside of the system. If we consider only the forces that are generated by particles within a system, that net force is going to be zero. So for instance, if I had me and the Earth, and I consider both of the force of gravity of the Earth pulling me down, and the force of the Earth pulling up on, of me pulling up on the Earth, if I included both of those forces would cancel out because of Newton's third law. But often, if we're just going to look about how the center of mass is moving in a system, we're going to have to include part of the forces as coming from outside the system. Okay, I think that explanation may have been more confusing than it was helpful. Okay, let's do a couple problems that are hopefully straightforward enough that they're not going to confuse you. Okay, so in this picture, this is one from your homework. We have three masses. M1 is 3 kilograms, and it has a position of 0, 0, 0 in the x direction, 0 in the y direction. Mass 2 has a mass of 4 kilograms, and it has a position of 2 in the x direction, 2 meters in the x direction, 1 meter in the y direction. And then mass 3 has 8 kilograms, and it is 1 over in the x direction, and 2 meters up in the y direction. Okay, now, the thing to notice is that for a system like this, my center of mass actually has to be somewhere in the middle of these three masses, and because this 8 kilogram mass has most of the mass in the system, I'm going to expect the center of mass to be somewhere over there. Now, if I want to calculate it, it's just a matter of where it is exactly. It's just a matter of plugging it in the formula. My total mass, which in the formula is the big M, would be the sum of all of my masses. So 8 plus 4 is 12, plus 3 is 15, so 15 kilograms. And then for part A and B, it's just asking you for the x and y coordinates of the center of mass. As I said, it's going to be somewhere in there, close to the M3. And the way we find our x center of mass is by going 1 over m plus x1 times the mass 1 plus x2 times the mass 2 plus x3 times the mass 3. And so in this case, that would be 1 over 15, 0 times 3 kilograms. So that's for this first object. For the second object, it would be plus 2 meters times 4 kilograms plus my x3 would be 1 meter, that's how far it is in the x direction, times 8 kilograms. Okay? So that's just using the formula, plugging in the numbers, and for part B of this problem, your y center of mass is going to be similar. You can go ahead and do that one. And then part C asks, if M3 is gradually increased, does the center of mass of the system shift towards or away from that particle? Well, it shifts towards. The center of mass is a weighted average, so it's moving towards where the most mass in your system is. If they're all distributed equally, then it's just going to be in the middle. All right, now, as we said last time, the thing that's special about the center of mass is that it acts like a particle. And I believe what I gave you last time, that problem was a little bit complicated. So let's try to do, this one is in your homework. I think this one is a little bit easier to understand. Now, here's the story. At t equals 0, you have a mass 1 that is 1,000 kilograms, and it's just sitting there. And in the story, its initial velocity is 0, but its acceleration is going to be 4 meters per second squared. Okay? Now, this is a one-dimensional problem. Everything is just moving in the x direction. But you have another particle, and at the beginning, they're both crossing this, let's call that x equals 0. They're both at x equals 0, but this mass 2 has some initial speed of 8 meters per second. Okay, so let me just write it in the same way where I have the mass 2 is going to be 2,000 kilograms, and the speed of the second truck is 8 meters per second. And the acceleration of this, I'm going to put a little 0 to indicate that this is at time equals 0 seconds. And the acceleration is 0. This truck is just going at a constant speed. Now, all right. Now, I hope you can see that because the position of the first object and the second object at t equals 0 they're both at the same position, 0. My x center of mass at time 0 is just going to be 0 meters. Now, what's a little bit confounding is that my center of mass also has an initial velocity and it also has an initial acceleration. All right, so how would I find the initial velocity of my center of mass? Well, my position of my center of mass is this. If I wanted to find the velocity of my center of mass, I would just have to take the derivative of everything. So my v of my center of mass at the beginning is going to be 1 over m, I'm just going off this formula, m1 v1 at the beginning plus m2 v2 at the beginning. So for us, the center of mass, the total mass is going to be 1,000 plus 2,000 is 3,000 kilograms. The v, I want you to notice that for m1, this term is going to be 0 kilograms meters per second, plus, and then the second one is actually going to contribute to that. So 2,000 times 8. 2,000 kilograms times 8 meters per second. Okay, so my center of mass has an initial speed of, or initial velocity, it's going in the plus x direction, of 2 over 3 times 8. So that would be 16 thirds meters per second. Now what might also be a little confusing is that this also has an initial acceleration. How do I find that? Well, I would have to use my F equals m, a center of mass. Well, let's think about it. This is the F net, so that's the total force on object 1 plus the total force on object 2. Now the total force on object 1 is m times a. F equals ma. So that's going to be 1,000 kilograms times 4 meters per second squared. So that's going to be 4,000 newtons. What's our acceleration or our force on the second object? Well, trick question. The acceleration of that second object is 0, so the net force on it is also 0. So in fact, the force on my first object is the total force on my object. It's the only thing that's accelerating. It's going to be the thing that is causing my center of mass to accelerate. So my total mass there is going to be 3,000 kilograms. My A of the center of mass is going to be 4 thirds meters per second squared. And that's my A center of mass. All right, so now look, I know what my initial position of my center of mass is. I know what my initial velocity of my center of mass is. I know what my acceleration of my center of mass is. Now let's look what the question is asking us. It says, how far is the center of mass of the automobile truck system from the traffic light at t equals 3 seconds? Well, I know all of this information. Now I can just use my kinematic formulas. So for part A, if I want to find my x center of mass, it's just going to be 1/2 A of the center of mass, t squared, plus v center of mass at the beginning times t, plus initial center of mass at time 0. Okay, so this would be 0. This would be 16 thirds. Time is 3 seconds. Acceleration is going to be 4 thirds. T is 3 seconds. So you just use the formula. And then part B asks, what is the speed of the center of mass then? Well, for that one, you could go ahead and here's your x. The speed is the derivative of that with respect to time. So it would be V center of mass equals A center of mass at times t plus V naught of the center of mass. Okay, so the tricky part was finding all of these initial values, and then after that it just acts like a regular old particle, and we can just do kinematics. All right, I say just, I realize the problem is a little tricky, so bear with me. Take a shot at your homework and give them a try, and we can look at some more on Friday. Okay, so that was the first part of what we did last class period. The second part of what we did last class period has to do with the impulse momentum theorem. And remember, the way that we defined the momentum was just the mass of an object times its velocity vector. So momentum is itself a vector. Momentum has a direction, and it's in the same direction as an object's velocity. And we rewrote Newton's second law in terms of that. So the way the momentum is changing, it's just the derivative of the velocity is acceleration. So it's just saying F equals ma in a sort of a fancy way. But what it allowed us to do was to realize that if we wanted to think about the way that the momentum of a particle is changing, we need to think about how much force is being applied for a certain amount of time. And we called that J the impulse. So if you take the average force being applied to an object multiplied by the amount of time that that force is being applied, it'll give you the change in momentum. And remember, this is going to be the mass times the final speed minus the mass times the initial, I guess I should say, initial velocity. Okay, so this problem, I think I did this at the end of the last video, so I'm not going to do this again. If you want to look at it, I think we already did this one. But the one that I want to just make sure that we understand is applying the impulse momentum theorem. Okay, so the impulse momentum theorem says that you take an impulse, you apply it, it causes a change in momentum. All right. So in this story, a force in the negative direction of an x-axis is applied. So our F is going that way, is applied for 27 milliseconds. Okay, so the delta T is going to be 27 milliseconds. Let me just write that in terms of seconds so we don't have to convert units later. 0.027 seconds. And it's applied to a 40 kilogram ball. So there's your mass, and, 0.4 kilograms, and the M equals 0.4 kilograms. And this ball's initial speed, V initial, is going to be 14 meters per second in the plus x direction. The force varies in magnitude, and the impulse has a magnitude of 32.4 newtons per second. Okay, now notice this force is applied in the minus x direction, and so my J would be minus, it would be minus because time is positive, so it would be minus 32.4 newtons times seconds. Okay, so part A asks, what are the speed and direction of the travel of the ball just after the force is applied? Well, you would just go ahead and use J equals M V final minus M V initial. You know your M, you know your V initial, you want to solve for your V final. Now that V final will have a positive or negative sign. If it's a positive number, that means the ball is going to continue to go in the plus x direction. If it's a negative number, that means it's going to have turned around. The ball will have It's just like in baseball where it comes in one way, it goes out in the other way. Okay? And then part C asks, what's the average magnitude of the force and direction of the impulse on the ball? Well, J equals F net, or F average, I should say, times delta T. So you know J, that's this. You know delta T, that's that. So you can go ahead and find the average. And of course, the impulse is going to be in the minus x direction because the force is in the minus x direction. Okay, so the problems are not terrible. It's just getting your hands into the new ways of talking. All right, so let's move ahead. We do have two new ideas today. And the first new idea is that without any external forces, the center of mass will not move. And I think I should say that more precisely. A more precise way to say that is that without any external forces, the center of mass will not accelerate. Okay? But let's say that we start out with the center of mass not moving. What happens if you have an F net is going to cause accelerations in the center of mass. However, if all of your objects are in your system, if all the objects causing forces on other objects are within your system, you have a Newton's third law applying. And every time you have an FBC, you have a minus FCB acting as in this picture. And your F net that applies for your center of mass is going to include both of those. So every time you have one of these forces in your net force, you have the other one as well. Those sum up to 0. So if you add up all the forces, you get just a system net force that's 0, which leads to a 0 acceleration. So unless you have forces coming in from the outside, your center of mass of the way that you've defined your system will not, let me just write that, will not accelerate. All right, let's take a look at an easy problem that takes part in this fact. All right, here's the story. A high school physics teacher also happens to be a junior hockey team coach. During a break at practice, the coach asks two players to go to the center of the ice with a 10-meter pole. And this is one of our patented massless poles that we only have in physics. So think of it as being, light styrofoam or something like that. A 40-kilogram player is at one end of the pole. Let's put that at x equals 0. And a 60-kilogram player is at the other end. So there's your 60-kilogram player, and that one is at x equals 10 meters. The players then start pulling themselves together by the rod and sliding on the ice as they move along the rod. When the two players meet, what distance will the 60-kilogram player have moved? Well, the thing to realize is the center of mass of the two players is not changing. This player gets pulled this way, the other player gets pulled that way. They're pulling on each other with the same amount of force by Newton's third law. So where is the center of mass going to be? Well, if we wanted to find the center of mass, it would be at 1 over m. So m in this case is going to be 40 kilograms plus 60 kilograms. That's 100 kilograms. Times m1 times x1. So that's in fact going to be 40 times 0. Plus m2 times x2. So that's going to be 60 kilograms times 10 meters. Okay, so our x center of mass is going to be at 600 divided by 100 is at 6 meters. Okay, so that's 6 meters away from the 40 kilogram. This distance then is 4 meters. When the two players meet, what distance will the 60 kilogram player have moved? He will have moved 4 meters. Okay? So I gave you one in your homework that's almost exactly this problem. Just different numbers, different scenario, but very, very, very close to this. Okay, so that's our first idea. Our second idea is that in this type of system where you don't have external forces, the net momentum is conserved. Okay, so F net equals dp dt. In your total system, that P would be the sum of all the M times V of each individual particle. You do a vector sum of all of them. And so if you don't have any, if the system net force is 0, so for instance, if the particles are only acting on each other, there's nothing from the outside of the system acting on them, then you're going to have a net momentum that's just constant. And so the important thing to realize is that we can add up all of the momentum of our particles before they interact. And it should equal the total momentum of all my particles after they interact. So you can imagine balls bouncing off of each other, or a car getting in a crash, or shooting a bullet into a block, or any one of those situations is going to be covered by this sort of consideration. So there is another piece of nomenclature that I want to introduce to you, and that is the distinction between elastic and inelastic collisions. So in an elastic collision, the idea that I want to put into your mind is that you have, for instance, a cue ball comes in at some initial speed, V1 initial, and it bumps into another ball, might have some different speed, V1 final, and then, V2 initial, and then they bounce off of each other, and so you have your mass 1 and mass 2. They did not stick to each other at all. You have a V1 final and a V2 final. And the reason that we call this an elastic is, it was very springy, and also the 1/2 mv1 initial plus 1/2 mv1 final equals 1/2 mv1 final, 1 v initial, v2 initial. So what am I doing here? I'm adding up the kinetic energy of the first particle at the beginning, kinetic energy of the first particle at the end, of the second particle at the beginning. And then you add up the kinetic energies of both particles at the end. Their speeds are going to potentially be different, but the total sum of our kinetic energy is the same. Okay, so that's what defines an elastic collision, and that is a very special case. That is not usually what happens. This only happens in cases like, pool tables, and that's about it. For inelastic collisions, you could have, for instance, a case where M1 is a first car and M2 is your second car, and there's your V1 initial, And they run together into like a stuck together mess. M1, M2. So your M3 there would be the sum of the two because they stick together. I'll just call it V final. What you would find is that if you added up the kinetic energy of this plus the kinetic energy of that, you would find a bigger number than the kinetic energy of the final structure. Okay, so kinetic energy has not been conserved. However, the real key point about this is that despite the fact that kinetic energy is not conserved in that type of interaction, momentum still is conserved. Okay, momentum is in fact conserved in either one of these. It's conserved in the elastic collision and it's conserved in the inelastic collision. So let's look at some examples. So what do we mean exactly by momentum conservation? Let's think about it in terms of our simplest possible example. This is the same story as if you ever went to a roller rink with a friend and you're both roller skating and you push off of each other. One of you goes this way, your friend goes that way, and you both have some final speed. So that's what's happening in this story. In this story, we have a 91 kilogram man, so we know the man's mass. 91. Wow. Lies on the surface of a negligible friction, so he's laying on an ice rink or something, and he shoves a 68-gram stone away from him. So M2 equals 0.068 kilograms, giving it a speed of 4 meters per second. So V2 final is going to be equal to 4.0 meters per second. What speed does the man acquire as a result? So we want to find V1 final equals question mark. Now, conservation of momentum tells me that if I take M1 V1 initial plus M2 V2 initial, so the momentum of the first object plus the momentum of the second object equals M1 V1 final plus M2 V2 final. Okay, so if I add up the momentum beforehand, I'll get the same as the momentum afterwards. However, if I'm looking at this momentum that I have, M2 times V2 final, is going to be a positive number, so I can calculate that right away. However, let me think about it. What speed do they have beforehand? Well, if they're just sitting there standing still, this speed is going to be 0. So this is going to be 0. And this speed's also 0, so that's also going to be 0. So I'm going to have a positive number equals 0. How does that work? Well, the way that it works is that the momentum on one of your objects is positive, the momentum on the other object is negative. How can you have a negative momentum? Well, it's just mass times velocity. A negative velocity means that the object is going to be going backwards. So if the stone goes forwards, the man will go backwards, and you can find out what that velocity would be. Okay? So this type of problem is not terribly hard to find. You would just solve for V1 final and set all that stuff equal to 0. Here's a problem that's a little more tricky, but still not too bad. Again, this is going to be one of those cases where it's an inelastic collision. You have less kinetic energy at the end of the story than you have at the beginning. As the two cars crash into each other, some of that energy gets converted into heat. And let's see how this works. Two identical cars were involved in a collision at an icy intersection. Car A was stopped at a traffic light. Okay, so you have M and M. They're both the same mass. This one has an initial velocity, V2 initial equals 0. When it suffered a perfectly inelastic collision with the back end of car A. With what speed did the two cars slide into the intersection after the collision? So it starts out going at some speed V1 initial equals V. And then afterwards they stick together. So we have a, here's our before, here's our after. Now we have 2m, because m and m have stuck together. So our total mass is 2m, and it's going forward at some v final. Okay, so all I have to do now is to add up my momenta of the objects before equals the momenta of the object afterwards. So m1 times v, let's just call it m times v, plus, what's the momentum of this? Well, if its speed is 0, its momentum is also 0. M times v equals 2m, that's the mass, times the v final. Now, luckily, our final answer doesn't depend on m, and you can see why. I'm going to divide both sides by 2m, and what I get is v over 2 equals v final. So that is my answer. Our cars are going to be going half as fast afterwards. Okay, so that's a totally inelastic collision. Kinetic energy is not conserved, however, momentum is conserved. Now, what I want to kind of preview for you, and I gave you quite a few problems on this, so the reason I mention this is that if you want to try to get your homework done, it's going to be good to take a look at this sort of thing. Some of these problems will use different sorts of ways of thinking about different parts of the problem. So here's an example of a ballistic pendulum. They use these to measure the speed of a bullet. And the way that it works is that you go ahead and shoot a bullet into a block that's hanging on a string. Okay? Now, the story that we tell is that as that block pummels into the bullet pummels into the block, you don't actually have energy conservation, because some of that energy of the bullet is getting transformed into, breaking the hole into the into the block, heating it up, all of that. But what is conserved is the momentum. So what you say is, at the beginning, I have momentum conservation when the this essentially gives an impulse to the block. So the momentum of this bullet is transformed into the momentum of the bullet block system. Okay, so I have mass of the bullet times v of the bullet. Sorry. M times v of the bullet equals the momentum of the mass bullet system. So it's going to have the total mass of that is going to be the mass of the bullet plus the mass of the block times the v final. Okay, so that v is going to be the mass of the bullet times the v of the bullet over mass of the bullet plus the mass of the block times the initial speed of the bullet. Okay, so you have some initial speed for that block. Now, after that, you can think of it as being an energy conserving problem. So you can think of this as just a pendulum, and the kinetic energy of the pendulum goes into the potential energy of the pendulum. So afterwards, you have a nicely swinging pendulum. You can measure how high the pendulum swings, and from that, you can infer what this velocity was. If you can measure the mass of the block and the mass of the bullet, you can infer then what the speed of the bullet was. Okay, so that's the game we're going to play. I don't think I want to do a problem with this because I didn't get to it in class today. But we'll start out our video on Friday doing something like this. And if you have further questions, make sure you email them to me. And I know this stuff has been a little quick, but hopefully we're going to make some progress. I'm trying to catch us up a little bit from our missed snow days. So what are our big ideas? When there's no net external force on the particles in a system, the net momentum of the system does not change. It's conserved. What's our other idea? This momentum conservation holds both for elastic and inelastic collisions. Elastic collisions are when two objects knock off each other and the initial kinetic energy is the same as the final kinetic energy. And inelastic collisions are when they hit, they might stick together or deform or something like that. And in that case, you don't have the amount of kinetic energy in as the same as the amount of kinetic energy out. And finally, we're going to look at a couple problems like the ballistic pendulum that incorporate different ways for different parts of the problem. So momentum conservation for the first part, and then energy conservation for the second part. Okay, so thank you for watching. Take a crack at your homework, and we'll see you next time.